Hello, everyone. Welcome back. We're going to continue on with Chapter 8 and then move on to Chapter 9, and we'll see how much we get through Chapter 10. We'll talk more about what that means for the homework. So before we begin, I wanted to review how to balance chemical reactions because I think there was some confusion between what is presented in the lecture slides and what I suggest. Um, the the formal rules in the lecture slides are actually not bad. But I had said before that I usually skip over them and I just tell you how I solve chemical equations, and it's pretty much the same idea. So we're just going to go over a quick example, maybe take 5 to 10 minutes to do this exercise, and then we'll move on with the lecture. Okay, so just look at my whiteboard here. So we're going to say, so let's balance this equation. So balancing chemical equations. So for example, what if I have this situation? So say I have calcium hydroxide plus phosphoric acid, and that gives me calcium phosphate. So let's actually go back a bit. Calcium phosphate. Oops, sorry, I already got the wrong coefficients here. Remember, phosphate is 3 minus and calcium is 2 plus, so we must switch the coefficients. And lastly, we have plus H2O. Okay, so actually, okay, I think that's okay. It's a little bit on the side, but I apologize for that. So my question is, what is the sum of the coefficients? So let's figure that out. So that's the question we ultimately want to answer, okay? So first thing you should do, so the first rule is we try to balance one element at the time, so makes things easier. So the easiest thing to do is to look for elements in the chemical formulas that are only present in one other compound. For example, in my case, I have calcium and phosphorus, because both calcium and phosphorus only occur in one other compound, right? So these all both occur in my other compound, calcium phosphate right here. So those are either one of those elements I want to balance first. You don't want to balance hydrogen because it's almost in all compounds, 3 out of the 4 compounds, and oxygen is even worse because it's present in all 4. So if you try to balance oxygen, it's going to get a little bit confusing because you also have to balance calcium and phosphorus at the end. So it's better if we balance oxygen and hydrogen last. So what you want to do is balance either calcium or phosphorus first because they are only present in one other compound. Okay, so if we decide to balance, so let's try to balance calcium, right? So let's see here. There are 3 calcium atoms. So we have 3 calciums on the left, on the right side, right? We have 3 calciums on the right. So let's try to balance calcium first. So let's balance, so let's put 3 in front of calcium hydroxide so we can balance the calcium that's on the right. All right, so now we have okay, so let's just go over here. So now we have on this side we have 3 calciums. We have 3 calciums, 10 oxygens. So you see, so I actually drew this a little bit wrong right now. Sorry. So the calcium, the 2 should come outside. So right now we have, so if we have 3 calciums here, that means we multiplied the already 2 oxygens. So we have 6 oxygens here. So there's 6 oxygens here. So 6 plus, and the 4 oxygens from the phosphate. So that's 10. Then we have 9 hydrogens from the, we also have it from the 6 plus 3 from the phosphate, or phosphoric acid, sorry. And then we have 1 phosphorus. Now on the right side, we have 3 calciums, 9 oxygens, 2 hydrogens, and 2 phosphorus. So now we see that we are balanced in the calcium atoms, right? So now that's balanced. So now let's move forward and balance phosphorus. So are any ever any questions? Always come to office hours. Balancing is a little bit tricky. At first, I mean, when I first learned it, I did not know how to balance at all, but I was pretty young at the time. And, you know, when in middle school, you tend to zoom in and out of focus during class is my excuse, but there's no excuse here in college because we're adults, we're mature, we should be mature, and we should absolutely focus on our studies to prepare us for our future careers. So in this case, balancing is it's really not, it's really like a trick. You just have to get used to it. There's really no you just need to practice, I would say. Okay, so next, let's balance phosphorus because that's the next element that's only present in one other compound, in phosphoric acid on the left and calcium phosphate on the right. So now let's balance phosphorus. So we balance phosphorus because it's the other element present in one other compound. Okay, so let's balance phosphorus. So what we have now is we're going to put a 2 in front of the calcium, in front of the phosphoric acid because there's 2 phosphorus on the other side. So let's do that. So we have 3 calcium hydroxide plus, so we're going to put a 2 here on the phosphorus for the phosphorus side right there. And now we're going to keep our calcium phosphate. Let's make sure I copied it all the same. Yep. And then plus water. Oops, let me just, I'm not very good with space today. Okay, so see here, now we have put a 2 in front of the phosphoric acid. We put a 2 in front of the phosphoric acid here. So now let's see if we have, now let's do some more atom accounting. So now we have 3 calciums, 14 oxygens, because now we have added 4 additional oxygens from the phosphoric acid. So there was going to be twice the amount of oxygen atoms. So now we add 4 more to our previous total, which was 10, 14 oxygens. Now we have 12 hydrogens. And now we have 2 phosphorus atoms on the left side. So now let's go to our right side. What do we have on the right? So if people want a more detailed like I actually pre-wrote a document about this, so I could post this tutorial that I've done, so I can post it on Canvas. It says 2 in case I am going a little bit too fast. So now on the right side we have 3 calciums, 9 oxygens still because we haven't done anything, 2 hydrogens, and now we have 2 phosphorus atoms. So now our calciums are balanced and our phosphorus are balanced. So now that's left is to balance our oxygen and hydrogen atoms. So we always leave those last because they are present in more than one other compound. So it's better to leave them last. Okay. So you notice that we need to balance both oxygen and hydrogen. So what coefficient can we kind of manipulate to do that? Well, you don't want to play with calcium phosphate because the calcium is already balanced. So if you do something to the right side for the calcium, you can increase the oxygen number, but that would be a little bit more complicated given that it also has phosphorus and calcium in the equation. So we look here, it also has calcium and phosphorus. So we don't want to mess with that coefficient. So we're going to keep that as 1. So whenever there's no coefficient specified in the space, you assume it's 1. It's never 0 because you can't react with 0 molecules or atoms of something. That just gives you nothing. So we have to look at our water. So we have a difference of 10 hydrogens and a difference of we have a difference of, oh, sorry, I think I wrote this a little bit wrong. It should be, no, I think I wrote it right. Okay. Okay, so we have a difference of 10 hydrogens and a difference of 5 oxygens. So we need to multiply the water by a certain integer to get to 14 oxygens and 12 hydrogens. And you can see that on the right side, if we ignore the water, we already have 8 hydrogens right here. So see here we have 8, sorry, not 8 hydrogens, 8 oxygens. So if we subtract 8 from 14, we need 6 oxygens more. And if we times 6 by 2 for the hydrogens, we get 12 hydrogens. So what we should put in front of the water is 6. So that's how we're going to balance this final, how we're going to balance the oxygen and hydrogen atoms. We're going to actually use the water and put a 6 in front of it. So 3, balance oxygen and hydrogen. So we have 3 calcium. So to kind of come to this conclusion, you really need to do trial and error. And if you do if you go first with balanced atoms that only appear in one other compound, then you should always come to this conclusion. And that's how we did the exercises in chapter 8. That's how we balanced the equations. Okay, so plus 2 phosphoric acid plus calcium phosphate. And then we're going to get plus 6 water molecules. So now on this side, we have 3 calciums, 14 oxygens, 12 hydrogens, and 2 phosphorus. Now we have 3 calciums here, 14 oxygens, 12 hydrogens, because 6 times 2 is 12, and 2 phosphorus. So now everything is balanced, and we have a complete balanced equation. So now let's add them all up. So this is what the balanced equation would look like. right here. That's our balanced equation. So remember, to answer our question, what is the sum of the coefficients of our balanced reaction? Remember, there's a 1 in front of this calcium phosphate, so we just add the integers, 3 plus 2 plus 1 plus 6. So that gives us a total of 12. So that is the sum of the integers. So most of the time when you balance the equation, we will not ask you this specific question, but if there's a specific question to be asked, like what is the sum of the coefficients of the balanced chemical reaction, you're going to have to choose a number, and then you have to remember that if there's nothing in front, explicitly in front of a compound in the chemical equation, you assume that it's a 1. So don't assume a 0. That is a common mistake. And a lot of people will miss this multiple choice question or multiple choice question like this because they did not take into account that there's an implicit 1 implied. And so that's a very common mistake amongst all incoming like chemistry students. So I encourage you to review balancing, and always remember that there's a 1 in front of a chemical compound if no other number is specified. Okay, so that was balancing of a tutorial. I'll post this little thing I made on Canvas, but that is how you would balance these equations like this. And you can do this for any type of reaction, so it doesn't matter. The rules do not change for a specific kind of reaction. So I would definitely practice these questions. In the homework, also, I'll post a practice final exam, so give that a look to give you some more practice with this. But you can also use the examples in the book, or just practice the homework a few times, the module a few times, if you're ever if you think you need more practice with this. But this will definitely be tested, probably on the quiz, definitely on the midterm final exam. So you'll have to write balanced chemical equations on a daily basis in chemistry. So it's important that you get this skill down. Anyway, that is it for balancing chemical reactions. So let's go ahead and switch gears here. So let's go back to learning about finishing up chapter 8. So my PowerPoint should still be up in chapter 8. All right, let's go. Okay. So let's talk more about chapter 8. Then we're going to move on to chapter 9. So we have about an hour left. So that exercise actually took a big chunk of time, about 15 minutes. That's all right. So let's just exit out here for a sec. I believe I stopped at neutralization reaction. That's right. Okay, so the last type of reaction we're going to cover is neutralization reactions. So neutralization reactions, they are, so the thing about neutralization reactions, they are acid-base reactions. So one of the most common reactions you may see is an acid-base reaction, in your body, and in cooking. We add acid and base stuff, they neutralize each other. When you clean up maybe a spill, you may use some acid or base if it's acidic in the laboratory. So it's the reaction between an acid and a base to form a salt and water. So the acid is any compound that has a hydrogen or can donate hydrogen ion and can be and that ion can be received by a water molecule. So the water will remove the proton and accept it and form a solution. So a base, in the simplest sense, a base is a compound that contains hydroxide ion, or OH minus. So we can actually measure the basicity or the strength of the base by how much hydroxide ion it produces in solution. So how much from water, how much of the ion that forms is hydroxide. And the salt is a product of neutralization. It does not contain the oxide. So it does not contain it does not contain an oxide. You know, if you had water, if you remove both protons, you get oxide. So it doesn't contain the oxide, proton, hydrogen ion. So we call hydrogen ion a proton. So you might hear me call it that. And that's because remember a hydrogen atom has one electron. So if we have and one proton, no neutrons. So if we have H plus ion, we lost its only electron. And so now it only has a proton. So we just call it a proton. So you might hear that throughout your chemistry education. You might hear that being referred to as that. So it does not. So when we have a salt, we form a salt which does not contain oxide, hydrogen ion, or hydroxide ion. It's a salt of whatever the acid's counter ion is. For example, if you had hydrogen chloride or hydrochloric acid, the anion would be Cl minus. So we react them, form water and a salt. Okay. So to get practical to this, let's write the equation for the reaction between sulfuric acid and solid aluminum hydroxide. So remember, sulfuric acid is H2SO4, and aluminum hydroxide, aluminum is 3 plus, OH minus is 1 minus. So we're going to have AlOH parentheses 3, and that will give us aluminum hydroxide. So always remember to put the state symbols. Sulfuric acid is in this case, let's just say it's aqueous, and solid aluminum hydroxide is a solid. So when we write those two out, we get aqueous sulfuric acid and aluminum hydroxide. So remember, the hydroxide, anytime you have hydroxide, that's a base. So our compound on the right is a base. Acid, when you have something called acid, assume it's an acid. So sulfuric acid, that's our acid, our source of hydrogen ion. So we get this. So sorry, there's supposed to be an arrow. I do not know why it keeps on not showing. So you get HOH. So see how the hydroxide ion took a proton from the sulfuric acid and it formed water. So we assume that all the sulfuric acid gets consumed and it forms the counter ion SO4. So SO4 is the counter ion here, and that forms an anion for aluminum. So actually, I don't know why it's Al2SO4. I think that's a typo, but let's just go on. I think that's a typo. I'm surprised I did not catch it. Sorry, everyone. Okay, so it put two aluminums. Oh, okay. Oh, okay. I didn't get forgot the parentheses. Yeah, I didn't get forgot the parentheses. So remember, aluminum's 3 plus, right? And sulfate is 2 minus. So that's why the aluminum has a 2. You have to swap the subscripts to make the charge neutral. So I believe this should be a 3 here. I'm sorry, everyone. I will fix those slides and post them, the updated ones, right away. So remember, that's our balance. Now we balance the equation. We have 3 sulfates on the right, so we need 3 sulfates on the left. So you just put 3 in front of sulfate, and everything else should balance. You have 6, 9 hydrogens on the left, and now you have don't have enough hydrogens. Oh wait, so this is not balanced yet. So they're gonna balance it. So you would put a 3 on the left because sulfate only appears in one other compound. So when you think of like polyatomic ions, just think of them as the whole unit. So balance the whole unit. Don't think of them as individual ions because that can get a little bit confusing. So whenever you have polyatomic ions, it's better to think of them as the whole unit and rather balance them one by one. But you can balance them one by one. It will still work. But my suggestion is just look at the whole formula unit for the polyatomic ion, because if you balance all that unit, you'll balance all the atoms all together at the same time. Okay, so we need 3 sulfate, 3 sulfuric acid molecules because we have 3 sulfate ions on the right. And there we go. Then we balance the aluminum because we have 2 aluminums on the right. So we have 2 aluminums right there. And now, since we have 6 hydrogens on the left, and we also have 6 hydrogens on the right, we need to put a 6 in front of the water to get 12 hydrogens. And that will balance out the hydrogens. And the oxygen should be balanced because on the right we have 6 plus 12, that's 18. And on the left we have 6 oxygens plus 12 oxygens, that's 18 oxygens on the left. So everything is balanced here. So see here on the last slide, the last thing they mentioned is the 6OH. So they group the OH together. And that's because you have, it might hard to visualize that. So I wouldn't actually visualize the OH because on the right side, the OH is actually turned into water. So, so it's actually like 6 OHs turn into water. And then you have 6 additional protons that come from the sulfuric acid. So that might be hard to track. So my suggestion is probably, if you were to balance the oxygen and hydrogens, look at the total number of hydrogens and oxygens in this case. So it may be tough to see the polyatomic ions that are getting balanced, but for those of you who can do that, I encourage it. But there's always ways to balance equations. But this is an example of a neutralization reaction, so that is what I kind of expect on the quiz, at least. For a final exam, we may not have you write it out. We may have you just kind of balance we'll give you the chemical formula or chemical equation, and you have to balance it out for us. Okay, so that is chapter 8. I believe that is the last slide. No. Okay, here's a summary of the reactions we talked about. So this is just going over the types of reactions we discussed. Combination, bringing 2 molecules together, form a new product. Decomposition, taking like a compound and decomposing it into 2 or more elements or compounds. Single replacement, I switched partners, element plus an ionic compound. So whatever my element is, a metal or a non-metal or hydrogen, I'm going to switch out the metal or hydrogen or the non-metal in this case. And then double replacement is where I switch the metal. It's basically between 2. It can be between between 2 variety of different compounds, but essentially what exchanges is partners. So basically one part of the compound switches partner with another part of the compound, and they kind of swap. They do that swap. So you form 2 new compounds. They may be a solid, water, an acid, or an aqueous ionic compound. So if it's an aqueous ionic compound, that means there's really no reaction. They just form in solution. But usually these compounds have solutions of negative and positive ions. So the last example, neutralization, that was an example of double replacement because we swap partners. If you look back here, we swap partners, right? The aluminum's paired up with the sulfate, and the hydrogen ion paired up with the hydroxide. So that's double replacement. Okay, so the key to doing these is just practice with the homework. Just looking at these descriptions won't help much if you don't actually get practice doing these types of problems. So that's how we actually learn new things and actually get understanding, is by applying it to different situations and different problems that we haven't seen before. Okay, so that is the end of chapter 8. Hopefully there are no, hopefully everyone, that wasn't too bad. Please do the homework, do it on time, because this will be a good review to study for the final and for the quiz. So if you study right now, you won't feel kind of pressure to cram information all at the end over the weekend because the final exam is next Monday. So it's coming up quick. It's probably most of your guys' first final because it's at 8 a.m. I believe it's still at 8 a.m. Well, I will double check. But please do study and please come to office hours. For office hours, I'm actually going to switch them from Friday and put them on Wednesday instead from 10 to 10 a.m. to 12 p.m. so people can have ask me questions before the quiz. And I have a feeling people on Friday, they just want to focus on studying and maybe finish up the OWL homework. So the OWL homework, unfortunately, I think there'll be some OWL homework due over the weekend, but that should be okay because it'll help you study. It'll help you study. So I think that's a good way to force you guys to study. So it's almost over, guys. Just hang on. I'm glad that most of you have kept up with this course because I think about only I think only one student actually dropped. So that's actually good news. Because last year a lot I don't think like a number of students actually I think just stopped coming to class, didn't really keep up with it. Because I think if they were just more concerned about passing the placement test, and that's okay. But you should also treat this as kind of like a dummy class because it's worth no units, so it won't affect your GPA, and it gives you a sense how college life is. So hopefully, I think most of you have treated it that way, and I appreciate that. So anyway, enough of the rant. Let's go on to chapter 9, which we're going to talk now about kind of like ionic equations, writing what actually happens in these chemical reactions and why we can predict them to happen in such a way. So let's go over that. So we are going to go over now we're going to chapter 9. All right. So we should get through half of chapter 9 today. Then on Thursday we'll take the quiz. Then after that, we'll talk probably the rest of chapter 9. See if we can get to chapter 10. I want to get to parts of chapter 10 because it's important. But for chapter 10, I think for the homework it'll be really short. So whatever we cover, I'll cover on the homework. And some parts of chapter 10 are really not that as important. So we'll see how far we go. All right, let's go to chapter 9. We're going to open chapter 9 now. Okay. All right, chapter 9 is chemical change. So we're going to talk about how to detect chemical change, and we're going to talk more about the classifications of acids. If this would load up, that'll be great. So the one thing in chapter 9 we can't ignore is I'm not expecting you to write full equations for single replacement oxidation reactions. That's something we will not cover. So some of the learning objectives we'll learn is distinguishing between strong electrolytes, weak electrolytes, and non-electrolytes. Give the formula of ions from an ionic compound when it's dissolved in water, and explain why some solutions of compounds may be as strong or good or poor conductor of electricity. And we're going to talk about stuff about how they engage in reactions, how we write the complete ionic equations, stuff like that. We'll talk about oxidation reactions, like burning hydrocarbons and all that other stuff. Okay, so let's just get to the material. All right. So remember, like when we connect a bulb to like a battery, the electrodes are what gives the complete circuit. The electrons to flow through the bulb. Excuse me. And that what causes the light bulb to so that completed the circuit, when the electrodes touch, that gives us a continuous loop for electrons to flow through. And you know that movement of electrons is what gives us electricity, and that's what lights the bulb. So if we don't have that contact or that conduction of electricity throughout the wire, there will be no light, and so you'll be out of electricity. So when they're non-contact, so you can think of ions in the same way. If we're producing a current, those ions will actually conduct the electricity through the solution, and you can use it as a power source. So here are some common examples. So say I have an electrolyte and I put in water, right? Copper chloride, put in water, electrons will flow, see my two electrodes in solution. Those ions are actually like the kind of the invisible source because you can't see them, but they're the medium on which we have a closed circuit to light the light bulb. So even though their electrodes are not touching, those ions mediate the communication for the electrons to be conducted through the solution and to the other electrode to power the light bulb. So we have a complete closed circuit. Now, ethanol is a non-electrolyte because it does not have any ions in solution. So when we dissolve ethanol, we do not make carbon cations. So the way to think of ethanol is we have CH3, CH2, OH. So the thing is, it does not dissolve like this. It doesn't form these ions, an OH minus. So this does not occur. So in solution, it's still in this state, in this form. So nothing has happened to the bonds. That's because it's a covalent compound. So covalent compounds, they dissolve in water. They can dissolve in water, but they don't form ions. So they don't form this carbocation, carbon cation, or hydroxide ion. That just does not happen. So we say ethanol is a non-electrolyte, so it will not power the light bulb. So because it cannot conduct electricity because no ions are present. But now we have a weak electrolyte, acetic acid. It can readily donate a proton in an acid and form an acetate ion, which is the leftover part of the acetic acid. So acetic acid won't completely dissociate into ions. That's why you get a weaker light, or poor. It's a poor conductor of electricity because there's no light. There's less ions in solution, and less likely electricity is going to be transmitted through this closed circuit. So there's a closed circuit, but it's not as effective. So copper chloride completely dissolves into copper ions, copper 2 ions, and chloride ions, whereas acetic acid only partially dissociates. So most of the solution here is still acetic acid, and only a fraction is acetate ion and H+, because it's considered a weak acid, which in turn is considered, which is also another name for a weak electrolyte, or a compound that only produces a minimum or a minimal number of ions in solution. Okay. So we talked about what electrodes are. They're like conductors by which electric charge enters. So electrolysis is the passage of electric charge through an electrolyte. So when we pass electricity through it, we can actually use it for chemical reactions. Electric current, we generate current by moving charges, moving electrons, moving ions. So the electric current is actually connected through the solution by those movement of ions because they conduct electricity. So the ability of a solution to conduct electricity is regarded as your prime evidence that your solution contains ions. So there must be ions in solution if you can get electricity to flow through it. So here's an example. So see here, we use electricity to cause the electrolysis, pass the electric charge through a solute, or solution, through an electrolyte. So through the solution, we can cause electricity to bounce through, and That will cause electricity to be conducted by these ions, as you see on the right here. And when they move, they're actually being in contact due to their charges. They're going to be attracted to the negative positive ends of these electrodes. And that movement of ions will transfer the electrical energy into this electrode, and see negative charge will travel back up and light the bulb here. So that is an example of how ions work in solution and how they conduct electricity. So pretty cool stuff, and pretty basic rudimentary concepts for batteries. Now batteries, are more high tech. They have more considerations of what do we make the cathode, what do we make the anode. We also give consideration to what types of materials are used in batteries, so they are safe for consumer use. So these always have applications for everything that's evolved. A few years ago, 3 people won the Nobel Prize for lithium ion batteries. So a very, very important contribution, not only for humanity and for advancement of society in general. So all these concepts we try to convey, they always come back to some chemistry being the central science and how it relates back to the real world. So there's always lots of applications for chemistry. But anyway, let's move on. Electrolytes. So strong electrolytes. So we consider a strong electrolyte any substance when dissolved in water yields a solution with a lot of ions. So it's a good conductor of electricity. So basically, almost everything is completely ionized, or ionization, or complete dissociation. So we separate our ionic compound into ions. So most of the form in solution is now, we say, separated or dissociated or ionized. A weak electrolyte is the opposite. It yields some ions, but most of the compound is still the compound itself and not the dissociated form. So we have a limited ionization or dissociation. So we call that a weak conductor of electricity because there's less ions being produced. Non-electrolyte is the negative case, where when we dissolve our substance, we produce no ions at all. So we call it a non-conductor of electricity. And there's no ionic movement. There's no movement of ions, so you cannot easily transfer that charge through the solution. Okay. So here are some solutions of ionic compounds. When ionic compounds dissolve in water, we create water and molecules of ions. So ions are identified we have molecules, and then we can have ions too. So ions are identified by separating the compound into respective ions. So common examples are ionic compounds. So sodium chloride. So sodium chloride, if we dissolve it in water, we will get sodium plus and chloride minus. So there are our 2 ions. So almost all salts are soluble in water. There are some exceptions, and we'll go over that. So if we dissolve copper 2 chloride, as we saw in the other slide, we get copper 2 plus ion and 2 Cl minus anion. So you might be expected to notice. So if you're dumped salt in water, right? You really at the end of the day, you don't really see the solid building up in the bottom solution, because the salt actually dissolves and the water helps in making that possible. So if you were to dump, sodium chloride and say like oil, you'll see the solid still at like the bottom or in the solution, in the liquid. So it doesn't actually form a solution. A solution is formed when you have a solid or a substance being, incorporated into the liquid, and now you can't tell water from the solid anymore. It's one homogeneous solution. So in this case, ionic compounds have very good water solubility, most of them anyway. There are some exceptions, but they form ions in solution, and we can't see individual ions. We can actually see the ionic compound because they're stable states, and once you have no water around, they just appear as solids. But ions, we can never physically see ions with our eyes. That's not possible. Okay, here's a solution. So see here that Yeah, so this is a depiction of what happens when we put salt in water. As time goes on, you know, like femtoseconds, very fast, water is going to be a solvate. We call it a solvate because water is the solvent. It's present in the greater amounts, so it surrounds each ions based on its polar nature, and it actually separates them from the solid, and that's what causes dissolution to happen. So when you pour salt in water, that water is actively sequestering each ion on part of the solid of sodium chloride, and eventually it will surround every ion, and then your solid will disappear and it will vanish, and all you have now is ions surrounded by water molecules, or what we call now it's solvated, or now it's forming an aqueous solution. So that's what we mean by aqueous. Every molecule is surrounded by water. And now once we separate those individual ions or individual molecules of something, you can no longer identify it as a singular or separate entity or existence. So now it's part of the water. So that's what we mean by aqueous. Separate are surrounded by water molecules right here. So this is a good picture to depict that if people are having trouble visualizing that. Okay, so for example, look here, if we have the solid blue copper 2 ions from copper chloride, you see here, if we were to dump this, we would expect if the water didn't interact with it, it would just be a solid at the bottom of this this transparent water in the beaker. But see here, as we add some of the solid here, the color disperses. So the copper ion gives that color. So you know you have copper in there if the water changes color. But see here now, the solid, you may think the solid is dispersed, but it's actually being solvated by the water molecule. So the water molecule is surrounding the ions here and dismantling it from its solid structure, and that's what creates our solution. So here, the ions are now sheathed by water molecules, and now we form a transparent blue aqueous solution here. So those positive interactions between the polar water molecule and the copper, it allows our solid to dissolve over time. Okay. Okay, so let's write the equation for potassium sulfate. So we're going to write the reaction as we saw before, like here, where we saw the dissolution of this solid from water to reduce the ions. We're just going to do the same thing for this exercise. So we're going to write potassium sulfate. So that's potassium sulfate, that's a solid. And we're just going to show an arrow with maybe water on top to show that it's being dissolved into potassium ions right here and sulfate anions. So remember, when you have 2 potassiums, you want plus 2 in front because the ion itself is K plus. Don't put K2 plus because that wouldn't make sense, because you'll be suggesting that there's 2 potassium atoms linked together, bonded, and they have a total plus charge. But that's not the case. It's actually only singular potassium atoms. So make sure when you translate this, put the 2 in front of the K, not as a subscript, because a subscript will denote a very peculiar ion, which will be wrong. So 2 potassium ions and 1 sulfate, because when you have 1 sulfate anion, remember it has 2 minus, so make sure your charge is balanced. If you get the charges wrong, that might be a point off. Okay. Okay, so let's write the ions present in solution for calcium nitrate. But we don't have to write the equation, just list these guys, these ions that are present here. So remember, calcium is 2 plus, it's from the group 2, so it forms a 2 plus ion. So this should be calcium 2 plus. And remember, we have nitrate. Since this is 2 plus and this overall compound is neutral, our nitrate must be -1 if we have 2 units of it. So we're going to write NO3 minus. So it forms calcium 2 plus and 2 nitrate ions solvated in solution. Okay, so we're going to talk about acids, more details about acids and what they are. Okay. So we talked before that it's a substance that has a proton that can be removed by water in solution. So we usually represent acids as HX. H is the proton. X is the rest of the molecule or compound. So and X can be any negatively charged ion produced when we lose the proton. So when we lose this proton, we form an X ion right here. And we talked about what X could be a lot in chapter 6 when we did nomenclature. So here we're kind of taking a step further and talking more about it. So when water grabs the H, it becomes this H3O plus, and that's called hydronium ion. It's called hydronium because it represents water picking up protons. So in solution, it's really not accurate to say that there's H plus in water, because the H would take the proton, and now it'll be the proton will be shuffling between a bunch of water molecules represented as H3O plus. So hydronium is actually the more correct way of saying H plus in solution, or with water as a solvent. If you didn't have water as a solvent, had any other solvent, H plus is perfectly valid. But since water is so polar, it's better to say that it's the hydronium ion. So X may be, a monatomic anion, or it may be a oxyanion like nitrate. And sorry, this should be on the bottom here. Sorry about that. So that should be nitrate, not 3 minus. That does not exist. I will fix that. So it might also be an ion that contains hydrogen. So we talked about that in chapter 6 as well. That may be ions that contain hydrogen. Remember sulfuric acid, it can donate one proton first to form hydrogen sulfate or bisulfate. Sorry, this should be a 4 on the bottom. And then it can lose another proton to give you hydronium ion and sulfate anion. So remember, when we have salts with this anion, but also ionic compounds are salts with this anion, like calcium sulfate, or in this case, maybe sodium hydrogen sulfate. So these can also form, they also serve as anions in ionic compounds too, as well. So when we're talking about carbon acids, so carbon-containing acids, they can have hydrogens like these hydrogens right here. So when the hydrogens are bonded to carbon, those are not the acidic hydrogens. The acidic hydrogens is the one connected to the oxygen. So there's this one. This one's not connected to carbon. It's actually connected to the oxygen. So that's something to keep in mind. But that's the one that gets lost. These ones are connected to this the carbon, one of the carbon atoms here, but those are not acidic at all. So compared to this hydrogen, these are considered not acidic and will never get lost, because this one will be lost first. There are ways to kind of pluck these hydrogens off, but we're not going to talk about that. That's a topic for organic chemistry, but that is probably maybe 1 or 2 years away from now. So you don't have to worry about that. So the general reaction for acids we have is HX reacts with water to form hydronium plus and H minus, or HX plus water gives us okay, so you could denote it like this. We can say HX plus water, but we don't have to put the water because it's a solvent. So we already assume that it's going to be dissolved in water, unless we specify something else. So we can say HX plus water gives us H plus minus H2O plus X minus, or we could say, simplify it to as just take the water out of the equation and just say, we put water, we know we're going to say it's going to be aqueous. We say aqueous, and so we assume it's water. So we just say the H, when HX dissolved in water will give us H plus and X minus. That's just saying another way if you don't, if we're trying to visualize without the hydronium, without the water present, this is a more simplified version. That in theory means the same thing, but when representing realistically, probably is not the same, because usually in solution, it's probably more accurate to say H3O plus because there's water shuffling the protons around. But don't worry too much about that that like nitty bitty detail. Okay, so now let's talk. We talked about acids and how to represent it in our chemical formulas. So let's talk about the classifications. A strong acid is equivalent to a strong electrolyte. So say I have sodium chloride, that's a strong electrolyte in water. A strong acid will produce almost complete ionization or dissociation in an aqueous solution, and it will lose its proton very quickly and very easily. So those are excellent conductors of electricity because they're like ionic compounds, dissolve completely, form ions. So they're very good conductors of electricity. So when we say major species, we say what species in solution is most present. So we have a strong electrolyte. Our major species are going to be the ions. So in solution, it'll be the greatest chemical particles. Minor species are considered what is not considered ionized. So when you have a strong acid, there's always going to be maybe some fraction of the starting compound that's still in its initial form or unionized form. So usually the minor species in a strong electrolyte or strong acid is the unionized molecule. So minor species in this case is present in the lesser abundance in our aqueous solution. So we'll probably talk about, do an example of this. Weak acid is the opposite. It ionizes only slightly or partially dissociates. And so in solution, we have more of the unionized compound than say the ions that form from it. So it does not release protons readily. So in this case, the weak acid will only donate partial amount of the proton from its compound. So they are poor conductors of electricity. So in this case, the major and minor species are flipped. Our major species are unionized molecules because it partially dissociates. So our unionized molecules are going to be present or left in the major amount. And then our minor species are the ions. Okay. So here's an example. So here's the macroscopic, here's the particulate level. So if we say we have a strong acid, strong electrolyte, see all the ions are dissolved and we have a great conduction of electricity. Now we have a weak acid or weak electrolyte. See here that this is our molecule right here. So this is our acetic acid molecules. So see here as there's more acetic acid molecules than say acetate, which is the conjugate base or the ion of acetic acid. See, there's only maybe two charges for a given amount of acetic acid molecules. Whereas in here, we don't see any HCl left. So we don't see any HCl molecules. All the chloride ions are all solvated, and also are all the protons. So all the ions here, so the major species are ions, whereas in the weak acid part, see here we have 1, 2, 3, 4, maybe five unionized acid molecules compared to the one ionized acid molecule. So this is considered a weak electrolyte. Not many of the species are dissolved or ionized. Well, they're dissolved, but they're not ionized. And here, all of the acid molecules are ionized. So that's the difference between a strong and weak electrolyte. And we have evidence for that based on our conduction of electricity here. Okay, so here's a classification of strong and weak acids. So these things you won't really have to, don't worry about what this row is saying. It's not important. What it's saying is that if you have a 1 molar solution, a strong acid will have, pretty much all dissociation. So this is percent ionization. So the takeaway is here, when you have a strong acid versus a weak acid, the numbers here should go way up. Whereas here, hydrofluoric acid is very weak. It will want to stay unionized. And here's the ionization equation. We use these arrows to represent which form is the major species in solution. So see here, it's pointing to the right. Longer arrow means that it has more ionization, or more that the products are more dominant in solution than the reactants. So more products will form here. And this is the opposite in solution. The reactants are more dominant than the products, so it's more stable for them to be unionized. So that's the difference between a weak and strong acid. This is the classification for major and minor species. Remember, strong acid, the ions are the major, and weak acid, the major species is the unionized form, because they're weak and they don't like to dissociate or form ions. And the minor species are just the opposite. Here is the reactant, or the unionized species, and here the minor species. And the weak acid is going to be the ions that would form in solution. So I kind of went over all those details, which are summarized here, but feel free to look at this here. Well, don't be bogged down trying to memorize word for word. Just think about what I said and try to kind of correlate that to the concepts and what a strong and weak electrolyte / weak acid, strong acid are, and you should be able to connect the dots. But if there are questions, please let me know. Okay, so there are a few common strong acids that I want you all to know. So here are well-known acids: nitric acid and sulfuric acid. They're well-known because they're used extensively in industry. Nitric acid, I say if I had a choice, I would not use nitric acid because it's a great oxidizer. So potentially very dangerous in concentrated amounts. So like we try to avoid using nitric acid or concentrated nitric acid. Just very nasty stuff. Sulfuric acid, you may know, it's used in car batteries. It's a great electrolyte. So it's used in car batteries. It's used for electrochemical processes, and it's a good source for strong acids in a chemical laboratory for doing experiments. So very popular. Then we have HCl, another very popular acid, HCl. Not as strong as the two on the left, but still, or not as prevalent maybe, but still a good acid. The reason why it's not as prevalent is because concentrated hydrochloric acid is only 37%. So it's very, so it's mostly water when you have the concentrated stuff. And that's because of the densities of hydrogen chloride in aqueous solution. So always weaker acid stream and weaker concentration. So that's why it has probably limited use. But you try to get more green conditions. You try to go away from strong acids because they have corrosive abilities, which tend to not be as good when considering the real world, let's say, outside of the chemical lab and outside into like applications. Not as great to have strong acids. Hydrobromic and hydroiodic, those are the group 7A, 17 acids. Those are rarely encountered. They have some niche or specific uses, but they're not as common as the other three I just mentioned. But these are some of the strong acids you should know. Chloric acids are even more rare. I've only heard about them in name and in learning, like you guys are. I've never actually used them myself in any chemical experiment. So they have very limited uses, I would say, and they're probably more expensive. Chloric is a strong acid, and perchloric. Those are the only two that are strong for the chlorine oxo acids. The others are not strong at all. So really the only chlorine, maybe oxo acid or derivative you probably have heard of is bleach, which contains sodium hypochlorite. So hypochlorite comes from hypochlorous acid, but hypochlorous acid is unstable, so you can't really isolate it and use it on a benchtop. You have to produce it in the reaction. So you have to produce it in situ, or what we say during the reaction. So during the course of the reaction, you produce it. Sodium hypochlorite, however, is stable in water, so we use that a lot because we use it in bleach when we maybe using it as a detergent. So those are the acids I want you to know, the strong acids. So those are pretty much the common ones I've learned, and those are probably ones that will be tested, and you'll see them probably a lot be upcoming in general chemistry too. Okay. So one thing we want to do is that when we think about how do we know we have a strong electrolyte or not, and how do we know if the strong electrolyte will produce the major species as the ions? Well, ions will always be the major species in solutions of all soluble ionic compounds. So that's one. So all soluble salts or metal compounds, ionic compounds, and all the 7 strong acids. So when you have solutions of the 7 strong acids, always think that they're going to produce lots of ions and near completion or near 100% ionization of the compound. Now, when you have neutral molecules, they are going to be the major species in solutions of everything else, primarily. So when you have neutral molecules and not ions, they are going to be the major species in solution of weak acids, weak bases, and water. Because remember, in water, they won't produce any neutral species in water, won't produce any ions. Weak acids, weak bases in water will only produce a fraction or very small portion of the compound will convert to ions. So the majority of the compound will be the neutral molecule, like we have saw in the previous slides. So those are the only times you'll see where the major species are ions versus where they're neutral molecules instead of ions. Okay, so do the homework. We'll go over this and you'll get some practice doing this as well. Okay, so let's write the major species in solutions of nitrous acid and chloric acid. So let's recall what nitrous acid is. It is HNO2, all right? And chloric acid, remember, that's one of those acids I asked you to memorize for in chapter 6, HClO3. So remember, O3 means IC, so chloric acid. So remember, nitrous acid was not one of those acids in the 7 strong acid list. So nitrous acid is a weak acid. So the major species in solution is the neutral molecule. Now, chloric acid was one of the acids I mentioned in that list. So it's going to dissociate into its ions, H plus and chlorate ion. So H plus and ClO3 minus. So those are how you would differentiate the major species in solutions for a strong acid versus a weak acid. Okay, so give this some more thought. The homework will definitely bring this up, and I may ask this question. I may ask something similar, maybe on the quiz, but just something to keep in mind. Okay. All right. So far we've been just writing the conventional equation. So it describes the reaction as a summary, but it does not really describe what's happening in water. So in aqueous solutions, it does not describe actually the chemistry behind of what's happening in water. Because remember we talked about, oh, the water will dissolve the compound to ions, but we don't actually look at that in the conventional equation. We actually just look at the neutral forms or the stable forms of the molecule, or the formulas for the aqueous ionic compounds and strong acids for soluble stuff. So we actually don't look at what's happening between the ions. So it does not describe the reaction that occurs in water, and also does not describe the chemical change that occurs. So it does not. So one thing it does not do is so an aqueous solution, remember, if it's completely aqueous, it should be dissolved in ions. So the conventional equation doesn't do that. So it doesn't actually describe the reactants or products correctly. So it's kind of, it falls short of describing like the nature of the species in solution. Is it just lead, or is it actually a solid, or what happened, right? So it actually, that's where the conventional equation actually falls short. So now we're going to talk about a series of different equations that are important in understanding what happens when we write out a chemical equation or the conventional equation. So ionic equations, we have something called ionic equations. So total ionic equation is the equation is written with ion formulas for all soluble aqueous ionic compounds and strong acids. So once for those kinds of compounds, we will write all the ions out because they're all soluble. And we do not write anything that is not soluble. For example, lead chloride is one of those ionic compounds that is not soluble in water, so it will actually not dissolve. And that's that has the reason why we probably won't really get into, but it has to do with the size of the ion, or the size of the lead and the chloride. Usually the size matters. So like if one size of an ion is different than the size of another, this solution will be disfavored. But I don't expect you guys to know that. But see here, we wrote everything that's soluble as ions, and everything that's not soluble as just the complete neutral formula, neutral molecule. So here, sorry, there should be a degree. I need to really go back and fix these. I apologize. Okay. So there's another term we might include. So when we write the total ionic equation, it includes all ions, not just the ions involved in the chemical reaction itself. So the ions that are not involved in the chemical reaction, we call them spectator ions. So that's exactly what they do. They don't participate in any reaction. They're just kind of there on the side when something happens. For example, like if someone witnesses a crime, they're not involved in the crime, right? They're just on the sides like bystanders or spectators. So, I mean, if they decide to intervene, then they'll be part of the situation. But if they don't intervene, they're just spectators, and they really don't do anything, right? They're just there. So that's the kind of the thing where spectator ions. Ions are present at the scene of a reaction. See, it just even links like that analogy. Scene of the reaction, but they do not participate in it like a bystander would. Okay, so those are spectator ions. So I expect you to know which ions in the reaction are spectators. So it's important that you understand how to write our total ionic equation as well as the next ionic equation that we'll talk about. So this is called total ionic or complete ionic. They're both the same thing. I prefer, I guess, total. I don't know. Doesn't matter really. So, but just know how to write it. We'll go over it. So net ionic equation is where you do not write any of the spectator ions, and you just write the ions that are involved in the reaction. So the net ionic equation is important because it indicates the reaction that's taking place. So we have lead 2 ion reacting with chloride ion to form lead chloride, lead 2 chloride right here. So notice here in our previous example that you see on the one side of the equation, we have lead, and one side of the equation, we have another ion. So every ion that appears on the left and the right, you can actually cancel out. So sodium appears on both sides of the equation, and nitrate appears on both sides of the equation. So we can cancel those out. So what's left is lead reacting with chloride to form lead 2 chloride, and that's exactly what happens here, right? That's exactly what's the net result. So you'll be expected to do that as well. So please, chapter 9, I consider it one of the other tougher subjects to kind of grip with. So and it's coming really late in the quarter. Just time constrictions and just different ways, just how slow initially the course went. So I apologize, but I want everyone to kind of understand this because it'll be very important in general chemistry. So it's very important you understand this aspect of general chemistry. Okay. So Ryan-Net ionic equation, I'll go over the pointers. So please include the state symbols, balance the equation. So first, write the total ionic equation by replacing an aqueous substance that has a strong acid or soluble ionic compound with its major species, which is ions. So don't write the neutral form, write the ions. Do not separate a weak acid even though its state is aqueous, into its ions, because it doesn't fully dissociate. So we can't say that. So we can't say it's dissociating. That's one common issue people make. One common mistake. They'll say, "Oh, this is a weak acid, so this is an acid, so it'll just dissociate into H plus and blah 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 minus." But that's not completely what happens. It just stays as the neutral form, and the ions are not present. So whenever I have an aqueous solution of weak acids or weak bases or neutral non-electrolyte substances, so that are not strong acids or ionic compounds, you're just going to leave them as their undissociated form. So do not change solids, liquids, or gases into ions. That does not happen, so don't do that. That's because we're just trying to make things as simplistic as possible that were represented in the reaction. So water doesn't change into an ion. If you don't have water doing anything and it's just a solvent, it'll just remain a liquid. So don't change it to any other state. So when we're balancing these reactions, we need to balance not only charge, so make sure both sides of the reaction are the same charge, but also the atoms are conserved in both sides of the reaction. Okay, so we'll go over stepwise what this means. Okay, so so there's two things you can do. Well, I would recommend first you write the conventional reaction, so what we've been practicing before, then write the total ionic equation. Then on the next slide, we're going to write the net ionic equation by removing the spectators. So if it's properly balanced, the spectators should be able to cancel on both sides of the equation. So you just take them out of the picture, and then you just write what's left, and that gives you our net ionic equation. So what you should do is reduce coefficients to the lowest terms if possible, and make sure everything's balanced again. Okay, so let's go over this example, and I think this might be maybe the last exercise we go over. So when we dip a strip of magnesium metal is placed in an iron 3 chloride solution, the magnesium chloride solution results in solid iron also forms. So let's write the net ionic equation for this. So wait, actually this example is an example of single replacement. So I think I was told out of the topics I'm supposed to cover, this one is crossed out. So actually I think I'm going to skip this one. But so we're going to skip this one, guys. So don't worry about this exercise. So I would say skip. So that's an example of single replacement because of metal or so just for I would say just skip this one, everyone. Okay, so this is something you also can skip, so don't worry about this slide for single replacement. It's crossed out on my list of topics to cover, so I assume you won't be tested on it. So let's skip that one. All right, so everyone, we're skipping these slides. This slide too, don't worry about this. All right, this slide you also can skip. So every slide I just said, please skip them. Okay. So, all right. So we are running out of time, everyone. So we'll pick up where we left off here. So this is going to cover oxidation reduction reactions. So that is, when you burn hydrocarbons, you ever barbecued, to produce the heat, you actually need like a fuel. So that's an example of burning or oxidation reduction of hydrocarbons. So burning is actually an oxidation of organic compounds. So when we see fires, they're actually burning because like grasses, they're composed of organic or carbon, and that just continuously burns. That's why California is always on fire, because the air is dry and you have just a bunch of this dead grass or dead trees or dead organic matter that can just catch on fire. So that is the end of chapter. That's where we stop in chapter 9. We'll finish that on we'll finish this chapter on Thursday. So that'll actually be the last lecture covering parts of chapter 9, then parts of chapter 10. So I'm going to edit the homework for chapter 10 because we're not going to cover completely all of it. And it's kind of, I think it's kind of long for having to do these last 2 homework assignments before the final exam. But I noticed that people are sending me like maybe they didn't have time to do the extra credit. But so if you can send me the extra credit, or if you want to do midterm exam corrections. So remember, for midterm exam corrections, I'm not awarding points for specifically what each person missed. It has to be one of those questions that's specified in the document. So pretty much the last part of the exam, the free response or calculation questions, because those were most commonly missed. A lot of people miss, multiple choice and true or false, fill in the blank, but those are pretty much all or nothing, so I can't award partial credit or grade correction for that. But for the free response and the calculations, I can actually reward you points for your dot process and showing your work. So that's why I'm allowing regrade or midterm corrections. But also, if you want to turn in an extra credit assignment, please do, because it's worth 10 points, and I will add that as extra credit to your score. So for homework, chapter 8, I believe, is due Wednesday at 12 a.m. Chapter 9, no, actually, I have to, actually, I don't think that's right either. But anyway, check Canvas. It'll have the due dates. I'm going to set the due date for chapter 9 soon. I probably won't make it till maybe like the weekend. So maybe chapter 9 and 10 will be due on the weekend. I know that's probably not ideal, but it'll help you study, guys. So I encourage you to do that. So do the homework because it'll help you study. And remember, homework is still part of your grade, so please be sure to do it. But anyway, guys, everyone, that is it. Please study. Please study for the quiz on Thursday. I already made an announcement about it, so I'm going to write the quiz. Please do the practice quiz, and I'll see you guys on Thursday to take the quiz. Then that'll be our last meeting. Time has flown by quick, so have a great rest of the week, great start of the week, and I'll see you on Thursday. All right, everyone. Bye.